Today, we're going to explore and prove the one-step subgroup test, an essential tool in abstract algebra. These tests helps us quickly determine if a subset of a group is itself a group by focusing on one main condition.
Understanding the one-step subgroup test. First, let's clarify what a subgroup is. A subgroup H of a group of G is a subset that forms a group under the same operation as G. So today we'll focus on the one-step subgroup test, which is often used to simplify subgroup verification. So there are types of subgroups. We have one-step, two-step, and finite subgroup tests. But for now, we will focus on one-step subgroup test. So what is a one-step subgroup test? So the one-step subgroup test allows us to determine if a subset is a subgroup by checking just one main condition. So this condition states that for any two elements, we have the A and B in H, no, we have A multiplied by B raised to -1 must also be in H. So this approach simplifies the process and saves time. So by proving, first we have the non-emptiness. So by the assumption, H is not empty, so there exists at least one element of H sub O is an element of H. So this is crucial because for any subset to be considered a subgroup, it must be contain at least one element. So that is non-emptiness. Second is the closure. So let A be an element of H by the hypothesis, since A times B is raised to -1 of H. Now we can show closure under the subgroup operation. So we have set B is equals to H sub O, since H is non-empty. And then A and B raised to -1 is equals to AH raised to 1 is an element of H. Now for all element of A is an element of H. Now which means H is closed under taking inverses. So that is the closure. And then the next is we have the identity element. So in identity element, since H is non-empty, so let H sub O an element of H, we need to show E is an element of H, whereas E is an identity in G. So we can express, since we have now established that H is non-empty, so let's denote that the element H sub O that we previously identified as belong to H. So we need to show that the identity element E of the subgroup G is also an element of H. So we can express the identity element as E is equals to H sub O times H sub O. Now since both H sub O and H sub O are element of H, and their one product must also be in H. So hence, the E is an element of H. So next is we have the final verification. So we finally we will verify that H meets all the criteria necessary to be considered a subgroup. So we have shown that H contains the elements. Now we established that H is closed under the group operation as demonstrated to our closure proof. So additionally, H is closed under taking inverses, which we confirmed earlier. So having established these three key properties, we conclude that H indeed satisfies all the conditions required for a subgroup of G. So now, why use the one-step subgroup test? So The answer lies in its simplicity, given simplicity and efficiency. So by focusing on closure, we with inverses, we avoid the need to verify each group property separately. This makes it a practical tool for checking subgroups. Okay, now so let's apply the one-step subgroup test with an example. So the example given is the group G is the set of integers under addition. This means that the group operation is addition and each element has an additive inverse. So the subset H, let's define H as the set of even integers, which includes numbers like -4, -2, 0, 2, and 4, and so on. So now first, whether H is a non-empty, or second, whether it is closed under operation with inverses. So here is the step-by-step solution. So first, we check the non-emptiness. So since 0 an integer is in H, we meet this requirement. So next, we verify for our closure. For our closure with inverses, for any even integers a and b and h, their differences, a and b is also an even integer. So this shows that h remains closed under the group operation. So it satisfies the one-step subgroup test. So therefore, h is indeed a subgroup of G. So in summary, the one-step subgroup test is a reliable tool to verify if a subset of a group is itself a subgroup. It's simple because it focuses on one primary condition, the closure with inverses. So remember, though that this test is especially useful when the group operation and subset align in a way that makes verifying closure straightforward. In cases with more complex operations, other subgroup tests might be necessary. So for your assignment, please answer and this question, and if you have any clarification regarding this topic, please comment down below. So thank you for watching.